Let me know when you see it live. Hubble Hangout and Hub. Hello, everybody, and welcome to the 225th meeting of the American Astronomical Society. My name is Tony Darnell. I work at the Space Telescope Science Institute, and we are here at the Northrop Grumman booth in the exhibit hall to talk about a really cool project called Starshade. And with me, as again, after a long time, is my old friend Alberto Conti. Now, we've got this awkward thing going with the microphone. I'm going to have to give it back and forth to him. And in a minute, I'm going to let him speak to us. But first, interact with us. Send us questions. Talk to us on Twitter, Facebook, and G+, as well as the YouTube page from which this is being broadcast. This is on our Hubble site channel. We're looking at your comments. If you use the hashtag Hubble Hangout, we will see that on Twitter. And I've got lots of people looking up for those tweets from you, as well as the comments on G+ and Facebook. So ask us questions about Starshade. You don't know what it is? We're gonna find out. So I got people here from Northrop Grumman to tell us, but before I introduce them, Alberto, it's good to see you again.
So you have to do this, which is a little awkward, isn't it? I have to wait to respond to you. It's great to see you again. We haven't seen each other for quite some time actually here. And so this is actually routine for us. So we should do this often, the old days. So we're going to do this. I wanted to mention, we're going to do this throughout the week. So you're going to do it half and half at the Northrop booth and half at the Space Telescope booth, which is fantastic. So we're going to talk about lots of topics. Starshade is just the first one. We have great people here from Northrop Grumman to tell you exactly what they are. And I'll leave it up to you. Let's get it on.
Yeah, so I'm glad. So you need to tell people what you're doing at Northrop, though. I don't think people know. What did you do? You left the institute to do what? What are you doing now?
I have a little strange title. I'm an innovation manager for civil air and space. So I work in a business development organization. So I have in my portfolio things like JWST, which I support. I can continue to support, but also things like we're going to talk about today, Starshades and maybe next generation flagships. So it's a very, very interesting job, very, very hectic, and I love it.
Yeah, well, we miss you at the institute, that's for sure. So, okay, let's get to the meet. Oh, one more thing. If you want to keep track of where we're going and what hangouts are coming next, the best way to do that is to follow our Facebook page, Hubble Telescope. Also follow NASA Hubble. He'll be tweeting on that, as well as I'll be posting the events on Google+. So that's how you're going to know which hangouts are coming up next. All the ones for today are already posted. We have a whole nother slew of them planned tomorrow. So. Okay, let me get to our guests. I have with me an astronomer from Northrop Grumman. His name is Ron Paladin. I had to look at your. I'm so bad at names. He is an astronomer at Northrop Grumman. Welcome. So tell us a little bit about what you're doing.
I'm the science manager for Northrop Grumman, and with regard to Starshades, I've been there since the beginning. When it was about 10 years ago, when the concept first came into being. We did some stuff with the University of Colorado, and what resulted from that was this concept of a Starshade.
Awesome. And also with me is Steve Warwick. He's an engineer building the thing. Hi, Steve.
Hi, how are you doing?
So tell us a little about what you're doing.
So most of what we're doing at the moment is testing the optics of the Starshade, seeing how the Starshade does what it's supposed to do, which is to block out the light of a star so that we can see the light from a planet, an exoplanet.
Well, welcome to both of you to our Hubble Hangout. I appreciate this, even though we're talking about Starshade. It is in fact a Hubble Hangout. So so Ron, let me get back to you a little bit. Tell everybody what this thing is. What are you doing? What is Starshade, and what are you hoping to accomplish with it?
Well, the big issue with seeing exoplanets, these are planets that are around stars outside the solar system. Planets are very faint, stars are very bright, so astronomers have been struggling for a long time with how to suppress that starlight and then see the planets around it. About 10 years ago, we came up with this concept for something that's very different from the traditional approach, which is to build an instrument and put it inside the telescope and get rid of the starlight through some sort of internal thing. This is a device that's fairly large, but it flies outside the telescope, and it blocks the light from entering the telescope and allows the planet to come through unencumbered. So it's sort of like putting your thumb in front of a bright light to block out the light so you can see what's around it. So yes, like that. And so this is just a very special, unusually shaped thumb.
I'll say.
It looks like a daisy with petals and such. And that's a mathematical design that allows this spot that it creates to be very, very deep and very dark. And so think of it as a traveling dark spot.
Okay, well, that's a really interesting concept. I mean, a lot of times, I know what you're saying about sometimes they have telescope tubes or optical assemblies will put something called an occulter in the light path to kind of block out just a little disc. Usually it's a cone shape or something like that that just sort of blocks out the bright spot of this, the bright star. Solar telescopes have these all over the place to block out the disk of the sun so they can see the limb and also the solar corona. So the stars, is it because the stars are so far away that the planets are, I mean, you can still resolve, even at, say, dozens of light years, planets that might be in orbit around a star with the light blocked?
Yes, I mean the big issue, and it is a hard thing to do. It's basically like trying to image a firefly a few centimeters from a searchlight. So it is a very, very difficult thing to do. But yes, with a large enough telescope and with something that can block out this light, the planets are going to be observable.
Awesome. So Steve, let me get you in on this. So have we started building it yet?
Not yet, not the space version at least. Okay. We've been doing some testing on the ground, and what we're doing there is we're taking a light source out to the desert. We've got a nice picture here. There's a light source over Ron's head over there, telescope in here, and what we're doing is we're using this bright light source to simulate a star. And we've got some other little light sources that simulate in the planet. We put a starshade, which is, you know, about that big, a 1% scale starshade, something like that, in between the bright source and the telescope, and we're checking our imaging with that. And we're showing that the computer models that we have for how the optics will work are very similar to what we're able to collect, the images we're able to collect in the desert.
Okay, so so we've got a proof of concept essentially already built.
Yes, absolutely. So one of the things with the starshades is as Ron mentioned, the very specific shape of it. We're trying to suppress the starlight to 10 to the 10, and that's a really difficult number. 10 to the 6 would be relatively easy. 10 to the 10 gets really quite hard. So there's a lot of questions about whether the model is going to be accurate. The optical model is accurate at that level. So there's some possible different shapes you can use. There's the issue of when you build this thing and you fly it in space, can you control the shape to the accuracy you need? So we've been doing some testing with what happens when the shape isn't quite perfect and you start distorting the shape. Does that affect the results that you're going to be able to get?
Okay, so you tested this on the ground and you said it works. Were you able to see anything? Any planet?
So when we're testing on the ground, we're looking at these LEDs. So what we're simulating a system. It's not quite the right scale for what you would be looking at.
Yeah, I misunderstood what you said about the test. Yeah, okay, you were using LEDs to do that and not actual stars, correct?
Yeah, we saw the LEDs.
Yeah. So yeah, sorry, I didn't hear that part.
More
so
importantly, we saw the LEDs like we expected to see them. So the whole point here is, because this is a new concept, this is something that hasn't been around for generations. It's something that really came into being in 2004 and 5. There's a lot of basic understanding that we need. And so these tests in the desert that Steve talked about are essential to start saying, if we model this is what we think we should see. And then we go out and empirically see, is this what we see? And then through those sorts of things, like Steve said, with putting in artificial distortions, if I can put in a distortion and predict what I'm going to see, then obviously I know more about this than if I put in something and I get something completely different. And so this is a very methodical process to go through and understand this optic, because it is an optic, and how it performs, what are the things that are tight tolerances, what are the things that are not very much. Oh, and here we go.
we have a model. Thank you.
This is what they look like in general.
No, I was going to just reiterate one thing. As Steve will show you in a second, describe the starshade, I want to go back to what the size of the problem really is, what are we trying to do, right? You're trying to find an Earth-like planet around a star, okay, and the planet is 10 billion times fainter than the parent star. So you're putting your thumb up there.
Virtually on top of it. So
And virtually on top of it, so there's very little separation. So that's the part of the problem. And so the shape is actually very meaningful. So I'm going to...
It's very pretty. I like it, yeah. But it's all black. You need to add colors and maybe a little smiley face in there, and that'll be... All right, tell us a little bit more about what you're holding up.
Okay, so what I'm holding here is one of the samples that we test in the desert, and as I mentioned earlier, this shape is critical to reaching that kind of suppression that we were looking for. we also have, just to shown how it worked, tested with a disk that's about the same size but completely circular. And what we see with the disk is that you get, as we expected, a bright ring of diffracted light from the main LED coming around that.
And that's just natural behavior of light going through anything. You want to tell us a little bit about diffraction?
So diffraction is the way that light bends around, or in fact any wave bends around a surface. In this case we're talking about light. When we've got a surface that is at right angles to the light beam, then it will bend around it. What's going on here is we're getting that same diffraction, but with this pedal shape, we're cancelling out the diffraction rings, so that we wind up with a little lower. All right. So that we can we're cancelling out the diffraction from different radii along a pedal, so that we get a much darker spot than we would with just a disc that was out in front.
So it was just one of the beauties of science that it turned out to be the shape it did.
That's exactly right. Yeah, absolutely.
Okay, so
mathematical shape.
Yeah, so the diffraction rings he's talking about, if you ever look at a star through a telescope and the secondary mirror, sometimes you can see little rings that come around it, and that's what they're talking about, canceling it out. And that can prevent you from seeing really close planets right near the star, so you want to get rid of that as much as you can. So, Ron, why space? Can we do this on the ground? I mean,
the problem with Starshades is that while it's a very efficient way to operate, it's a very large baseline. And so even in our desert test,
what do you mean long baseline?
The distance between the telescope and the Starshade has to be very large compared to the size of either. So, for example, in the desert, it's a couple of kilometers different distance between the Starshade and the camera.
So this was sitting a couple of kilometers away from the telescope you were testing.
Right. And so in space, because we're dealing with bigger telescopes and bigger things, you're talking about a 30 to 60 meter diameter Starshade tens of thousands of kilometers in front of a telescope. So it's a very long arm that is holding that thumb. And so they're independent. They're traveling together. So it's formation flying, but one that's relatively straightforward. And that's what allows us to have the really small spot, so we can cover the star but not cover the planet.
Okay. So we haven't. You've tested it, but we haven't actually started building this yet. Correct?
Not as a space mission, no. I mean, it's pretty critical that we know exactly how this works before we go spending, government money.
Right. So this is.
But we have begun testing components, because in parallel to the desert test, which are testing the optics, we and people at JPL and other people in the community are testing other aspects of this. Okay. How would we build it? How would we deploy it? What materials should be involved? So those are going on in parallel. They're not at the level right now where we would be using space equivalent hardware, but it's the first stages, like with the optical testing, of testing how in some number of years would we actually build this to fly in space.
I wanted to go back to something that Ron just said, which is not only the distance between. Oh, I hear a cell phone. That's all right. That's all right. So not only the distance between the telescope and the Starshade has to be over 10,000, thousands of kilometers, or 10,000 of kilometers, but actually the shape, the size of the Starshade is also relevant. So this is not. This is a clear model. It's very small. So maybe both you and Steve can give us an idea of how big. Would the telescope be? Would the Starshade have to be in order to act as this famous thumb?
Yeah, and also this is kind of solid material. You're not going to make it out of solid material, I don't think either, right? So.
No, I mean, I think the right now what we're looking at is something that is a membrane suspended between some sort of structure. But that's part of what we're looking at, is how we would go about doing this.
Anything like the JWST heat sun shields?
Yeah, something very similar to the JWST sun shield. And one of the interesting aspects of this is that one of the tests we will be doing over the next couple of years is, if I have a membrane, it's really light and therefore this thing doesn't have to weigh as much. But how transparent is it? Because even though if I look at a piece of mylar or whatever that I would use, it seems opaque. As Steve said, we're talking about 1 part in 10 billion. We need to make sure that it's actually opaque to that level. So there's lots of interesting tests that are going on.
Okay, so Alberto,
go back to what's the size of the.
Okay, so let's go back to the size of this. So tell us a little bit about how big these things are going to be.
So in the space application, we've looked at everything from 30 meters up to about 80 meters, and it depends very much on the telescope that you're working with. The other obvious problem that you've got is there aren't many photons coming from the planets that we're trying to observe. So you really want to get a large collecting area. You make the telescope larger, then the starshade has to be larger to be able to give the dark spot that surrounds the entire optics of your telescope. So there's lots of discussion here over the last weekend, and I'm sure there will be further discussion about the next generation telescope, the next generation telescope, the one after James Webb, and how big that will be. If you've got a 8-meter optic or 10-meter optic, then this starshade should be around 80 meters diameter to be able
80 meters, wow.
the dark spot.
Yeah, we're going to have a hangout on the future of space telescopes too a little bit later this week, I think. So we'll talk about that as well. So does the telescope have to be built to? You're building the Starshade now, and you're going to be able to build it in different sizes depending on, you said, the telescope that it's used with. But if I want to use a Starshade on my telescope, do I have to design my telescope to specifically be compatible with this? Does it require, for example, a certain field of view?
Not really, no. I mean, it will work with practically any generic space telescope, because you know there's lots of those lying around. But
I'm going to launch a C8. That's what I'm going to do. Either a C8 or a LX200. Yeah.
Yeah. So it should work with practically any space telescope. The only caveat to that is you need to know where the two things are. You need to know where your Starshade.
You've got to line them up.
Yeah, you've got to line them up. You've got to know where your Starshade spacecraft is. You've got to know where your telescope is. So the benefit is having a beacon on your telescope so that you can detect where you are relative to each other.
Oh, that's an interesting point. So how would that work, Ron? I mean,
There's one other aspect of this, is that, as I said, this is a traveling dark spot. That dark spot has a diameter. So you also have to match your telescope that it needs to sit inside the dark spot. We don't really care where in the dark spot. But if I have a dark spot that is, let's say, 5 meters across, and I have a 10-meter telescope, that's not going to help a whole lot.
So I do got to keep these things in mind when I build my telescope.
That's the only thing that it does require, is that the telescope has to fit inside the dark spot.
Okay.
And I can adjust this to be the size that it's needed. So if you have a 4-meter telescope, I can give you a 5 or 6 meter shadow. Or if you have a 10-meter one, I can give you a bigger one. But that's where the scaling size comes in.
Okay, so you said it's a movable dark spot. How do I move this thing?
It operates with propulsion, more likely than not electric propulsion, and I move it around the sky to align with sort of, yeah.
Like what? Rosetta, right?
Rosetta or Dawn and that sort of thing. So those sorts of things. So existing technology.
So you got to be patient to point this thing, right? I mean, if you want to, and you're going to have to somehow coordinate that with your telescope. It's going to have to all be linked together. You're going to have to. Right. And you're going to need to be. I want to now look over here at this part of the sky. It's going to take a while.
Right. And we look at, essentially, it's a traveling salesman problem. Is that we have a bunch of stars in the sky that we want to look at, and we can go from one to the next in some plan, and then therefore optimize the time. The nice thing about Starshade, since it doesn't require any special anything on the telescope, that in between those positionings, the telescope can be doing other astrophysics. So it's not one of these things where I'm dedicated to do this. The throughput of the Starshade is very high, so when I do finally align, I can get my data very quickly and then have it move on to the next one. And so it becomes basically how energetic of an ion propulsion system you have and how far you are away and this sort of stuff. But very doable and very much within giving you the right number of stars that people would want to survey.
Oh, that's awesome. So, Steve, I don't know if this is your expertise or not, but I'd like to ask you a little bit more about this ion drive. Can you tell us what they're like, how they work?
So not my area of expertise, but you are basically driving xenon gas out of the back of the thruster, xenon, depending on which side of the Atlantic you. Xenon. I'll call it xenon. And that's you're using electric propulsion to do that. So you're basically charging the particles and using the charge between two plates to pull the xenon out the back of the thruster.
So is that the limiting factor of the lifetime of a Starshade, is how much gas you put in it?
That would definitely be part of it. Because you were only able to look at planets, you've got a limit of how close you can look to the star, because that's the size of the dark spot, and we're talking of the order of 100 milliarc seconds, something like that, maybe 60 milliarc seconds, something like that. So what that means is when you're looking for habitable zones, you're only able to look at the nearest 200 or so stars, maybe 500 stars, because once you start looking at stars that are further away than that, then that angular separation between the habitable zone and the star starts to be too small. So Yes, it does have a lifetime, and that lifetime is based on fuel. But your point would be that to design a mission that can, in its lifetime, get round the stars that give you the best chance of finding, a Earth-like planet in our neighborhood.
Okay, he said habitable zone.
All right. Okay, habitable zone. This is what has become sort of the standard measure. And it's consider, we believe that water is essential for life. So the habitable zone is basically the area around a star where liquid water can exist on the surface of a planet. So if you go too close to the sun, it gets real hot. You evaporate all your water, so you get things like Mercury and Venus. If you go too far from the sun, you get ice freezing or water freezing out, and you get Mars and then Jupiter and beyond. So there is a narrow region around every star in which the temperature is just right. So it's also called the Goldilocks zone, where it's not too hot.
Unfortunately.
It's not too cold. It's just right. And so that's what people are looking for.
Yes, and we've talked at length about why liquid water is important. You may not think it's all that big a deal, but liquid water is where we start, because we know, at least in the one spot where we know there is life, it is vital. So we may as well look for what we know works. So that's why liquid water has been so important in our search for life. Ishan says he's got some social media stuff going to tell us. Daniel Nasato of Google Plus wants to know, how do you get the Starshade and the telescope to orbit in sync when they're thousands of kilometers apart? Who wants that one?
Sure. Great question. You can't do that around Earth. So your options are that you go to L2, which is where the James Webb Space Telescope is going.
And a lot of other things, it seems.
Yeah, and a lot of other things. So L2, that is a gravitational saddle that is in line with the sun and the Earth, and it's about 1 million miles beyond the Earth from the sun. And the gravity area there is pretty flat, and so your gravity difference between what's affecting the Starshade spacecraft and your telescope spacecraft is very minor. So you don't need that much fuel to hold the position between the two. There's other options as well. Earth trailing orbits or Earth leading orbits would also give you a way of doing that.
Really good question. I was going to ask it myself, but you got to it. You got another one, or is that it for now? Okay. So keep them coming, guys. We're monitoring. We got you covered. So, I guess so. We're in the planning stages now. Is there some kind of and presumably Northrop Grumman is building this thing for space at some point. Is there anything we're waiting on to make further progress on this, or is it?
Well, I mean,
I guess what are we ready to move to the next phase?
We are moving to the next phase. So the desert tests that we are in the process of doing, and there's still more to do, are establishing the optical properties. So we're understanding now what our tolerances are. We're getting empirical measures of theoretical calculations. So we're combining that so we understand how it works, what's needed to make it work, what kind of tolerances we need on the thing that we're going to build. And as I said, in parallel, we're also starting to look at how we would deploy this, how we would fit this into a fairing. So all those are starting to converge. And so over the next few years, we will learn more about this. Our understanding will grow. And at some point, hopefully within a couple of years, we will be ready to do some sort of demo test or something of that nature to go to the next stage. So this is a broad reach project right now, because we're looking at how it works optically, how it works mechanically, what are some of the issues, as per the question from there, what orbits we should go into, what those constraints put on things. So all those things need to be looked at. And so it's a lot of work to do, but it's coming together very nicely, and we would hope in a few years to be ready to start looking at a space-based, at least test, if not demonstration.
Okay, so in a couple of years we might be testing. Anybody want to prognosticate when this thing's going to be in orbit? Come on.
That's really up to NASA and how they...
Well, what's this? Is there good support for NASA on this project?
Yes, very good. And so NASA has been very helpful from the very early days. NASA's been involved in the discussion. Some of the demonstrations of how the deployment works were done at JPL with Northrop support and stuff. So NASA's very key to this, very important, and supplied both great intellectual property, but also the resources and the facilities to do some of this stuff.
The Starshade itself doesn't seem like it's that expensive to make. I mean, compared to some of the other things that go up into space, this might be a pretty economical thing to build, right?
Well, and a lot of that depends on what we find over the next few years. I mean, we are looking at tolerances and other sorts of things. We hope it will be very affordable. At this stage, it's probably a little early to say, absolutely, but, yes, indeed. Well, we think this is a very good way to go forward. We think this may be one of the better ways to find out if there's life outside the solar system.
No. Oh, okay. He took the words out of your mouth, did he? Okay, cool. Well, to me, what worries me are the space telescopes themselves. I don't know of a lot other than, say, WFIRST and maybe something down the road. We got to start now thinking about you're building Starshades, but we got telescopes to build to use these things. So that kind of worries me a little bit. I'm not sure.
And I guess one other aspect of this, the other big advantage of a Starshade is since it's an independent operator, it's an external occulter, an external coronagraph, it can actually operate with multiple telescopes. So if we had 3 or 4 telescopes at L2 right now, in principle, we could operate a Starshade with each one. So, one could look at using telescope number 1 to do one thing and telescope number 2 to do another thing. We just need to then move the Starshade in line with the telescope.
Well, what about JWST?
Certainly, one could in principle do that. As Steve said, the one big issue with this is the easiest way to align the two is to put a beacon on the telescope. So I know where the telescope is if I'm the Starshade, and the telescope knows where the Starshade is. If both those there, then it becomes really easy. Right now, there's no beacon on James Webb. So.
Alberto, you need to add that as a feature on JWST.
Yeah, that would be an interesting feature. I don't think it's in the plan, but it would be an interesting feature. So, but we'll have to see. It's
JWST is going to be looking at exoplanets.
JWST will look at, but remember, JWST was built to look at spectra for exoplanets, right? And so I think it's a kind of different kind of observing, right, that you want to do in terms of what you want to get out, right? And so it's also not going to look at, JWST doesn't have a resolution to look at Earth-sized planets, right? So you're going to look at hot Jupiters, for example, right?
So, Ishan, do you have anything for me? Golf Addict 75, YouTube. How small of a planet will it be able to image? Who wants that one?
I'll take that. The issue is that's dependent on how big of a telescope. As Steve said,
the resolving power of the telescope primary.
And how these planets are faint. So, but with a big telescope and a suitable Starshade, one should be able to image Earth or smaller planets.
So Earth-sized or smaller. And but you are limited by how close you can get, correct?
That's correct. So yeah, there's an inner working angle, 65 milliarc seconds, probably about right. Then it depends. Your Goldilocks zone depends on the brightness of the star. The type of star you're looking at. So certainly on some of them, like the M dwarfs, that area may be too far in for a Starshade to be able to work. But stars that are like our own star, then yeah, absolutely. There's 200 plus targets that we could go after with this.
Okay.
I just want to add, and you know that there's a lot of interest from NASA, from lots of other folks to actually look at planets that size, right? That have water in the Goldilocks zone. So I think it's not a surprising answer that we want to aim, for a 10 to 12 meter telescope, for example, in the future after JWST to those kind of planets, right?
Okay. Anything else, Ishan? Okay. So I want to get to a little bit about. So that's a little bit about Starshade. I want to thank you guys for giving us an update on that. But I want to talk a little bit about Northrop Grumman and why you guys are doing this. And we were talking last night, Ron, about how early career scientists, when they're coming out of graduate school and maybe going into postdoc, we were talking about how competitive that is. But actually, there's other career paths. You've both chosen industry, or at least you're working at Northrop Grumman. Can you talk a little bit about the opportunities that might be available to younger people? And I'm going to let Steve go first, and then I'll go to you, okay? Just maybe the idea is, I think, to let people know that it's not always about academia.
No, absolutely not. Our team, the team that works for Ron, I believe we've got four astronomy PhDs on the team.
Alberto's one, right? You got astronomy? Oh, you're not on their team. It was revoked, right?
Yeah. So that doesn't mean you're necessarily doing astronomy. You're doing engineering or interface to a customer like James Webb. Obviously, for James Webb, there are hundreds of scientists who are the customers for the James Webb Space Telescope. So something that astronomers working at Northrop Grumman have done is be the interface to those people, speak the science language, and learn a little bit of engineering and speak to the engineers too, and be that bridge so that us as engineers can understand properly what we're trying to do.
So how would it compare, do you think, Ron, with academia versus working in a company?
Well, it turns out I can give you a unique perspective on that.
That's why I asked you that.
The first third of my career, I was an academic, doing basic research, publishing papers. I then joined NASA, and in the middle third of my career, I was a NASA civil servant working at the Goddard Space Flight Center. And then I got a call one day from someone saying, "Did you ever think of working in industry?" And so the last third of my career is now in industry. And so I think one of the things that I think Starshades illustrates is the ability of a combined science and engineering team to solve the problems. One of the things that we went from over 10 years, we went from literally the laughable fringe. The first time we presented this paper on Starshades, we were actually laughed at because this is a chuckle, to now one of the baseline architectures. And the reason we were able to do that in such a short amount of time is we had a really nice integrated science and engineering team. The scientists contribute the science, the engineers contribute the engineering, and that combination of those two disciplines really allowed us to solve problems far faster than anybody ever thought we would solve. And so that's really the key, I think, to success for Starshades, is the ability of an industry, government, and academia team working together arm in arm to go forward. And that's really been beneficial and really got us through a lot of problems very quickly.
Okay, so Alberto, you're in that club too. How about you give us some comments on that?
I completely agree with what both these guys actually said, because it's absolutely true. So I just came from a panel called Careers 101 when I gave my perspective exactly about this, right? And so exactly along the lines of what Ron and Steve actually said. But one other thing that I wanted to add is also that sometimes the need for talking to engineers in a language they can understand and translating those requirements that are from science, for example, into engineering requirements is something that really is sometimes missing. So if you don't have that, your project would not really go very well. And so people like Steve, people like Ron are they're mediators, if you will, they're translator, right? They translate some requirements that come from astrophysics. What is the science that you want to implement? To this is how you actually build this, and then they argue for a while, and then they compromise. And actually, that's part of a team. A successful team actually is a team that can draw from the science requirements and understand how you implement those requirements while pushing the engineering at the limit. We do this every day for JWST, but it's a very successful thing that we do. And I think actually there's a great partnership that has to be had, in between industry, academia, and engineering, just because of this.
Yeah, and I just wanted to make that point because I know a lot of people think there's really only one path in science, in astronomy. You go to get your graduate or your undergrad degree, you get a graduate degree, you get your postdoc, you do the postdoc work, and then you hopefully get a job as a tenured professor at some point. But that is a highly competitive and a difficult way to go, and it's not also the only way to go. Yeah, and that's the point I really wanted to make.
Well, the other aspect of that is, in academia, when I was there were some very compelling problems, some really stimulating, mentally stimulating, intellectually, worthwhile things that I did. When I joined the government, there were also things there, and now in industry, there's also equal number of compelling things to do. So the real thing is, you want to work on something where you have the ability to contribute, where you have some contribution to something important. And at least from my career, I was able to do that as an academic, I was able to do that as a civil servant, and I was able to do that as a member of industry.
I just want to add one thing, which is the reason why people are, like, let's say, astronomers, for example, at companies like Northrop Grumman, is because their skills are in problem solving. They've been given a problem that no one else has seen before, and they can actually walk it through, right? And it's the same thing for engineers. They're bright engineers that can solve, they can solve very, very, very hard problems, and they're hired not because of the specialty, with which they did their thesis with. I did my thesis in, numerical simulations. Well, maybe it's not going to be very useful, but we have a way to approach problems that is not common, and that's actually what's worth, money and work to a company.
Well, that's also why a lot of physicists go into finance too. I mean, they solve problems using their skill set. Ishan, do you have another one to add? Ram Samurai. 2 questions on YouTube. How long can a Starshade be kept in space? And can you? Oh, good. We didn't cover that. A good one. And can you give us a simple explanation of how you unfurl it? What was the first one again? I forgot. How long? How long does it stay in space? Who wants that?
Sure. How long it stays in space? Purely driven by the fuel, the thrusters, the size of the tank that you're able to take with you. We would expect to make a mission that was 5 years, or maybe a little longer than that. That would be design mission.
Right, and we talked about that a little bit with the gas for the electron drive. Unfurling it.
Okay, so there are a couple of ways that we can do this. Obviously, unfurling is a critical problem. You're talking about making something in space that is 50, 60, 70 meters across, and rocket fairings at the moment are 5 meters across, or if you use the space, the SLS rocket, then maybe a little larger. So you need to unfurl the Starshade when you get on orbit. A couple of ways of doing that. We got some technology that was used for, and still is used for, unfolding antennas, mesh antennas in space. And that's it's called a perimeter truss design, and it expands with a ring of struts around the edge. So all the struts are wrapped up into one core, and as you drive a motor, these struts expand out into a ring that forms the center of a Starshade deployable design. Then what we have is the pedals attached to the edge of that perimeter truss that are start vertical, and as the truss pushes out, they rotate to be flat. So that's probably the easiest way to describe a deployment at the moment.
And presumably that would take a long time.
All right. If you look on YouTube and look for Starshades and deployment, you will see about a third scale demonstration that was done last year, I think. And so you should be able to watch it. It's on a number of YouTube sites. So just look for Starshade deployment on YouTube, and you'll find a demo. You'll find a video.
I'm glad you mentioned that. Thanks.
And then the next thing you can actually see, there's actually a video of a deployment that JPL put together. I think the full, after its rendition, but it's actually nice. It gives you an idea of how you would unfurl. Yeah,
because there's both a artist simulation and some real demonstrations. This gets back to your earlier comment about moving forward. This now has gotten to the point where we have a little bit of hardware being demonstrated, and we're moving forward in parallel with the desert test.
Awesome. So yeah, unfortunately, folks, this is not a hangout on air like we're used to doing. We don't have the technology to share our screens here. We're just streaming live from one spot. So definitely go to YouTube and look up Starshade, and all kinds of animations will come up, and you'll be able to see this deployment. I'm glad we brought that up. Do you have anything else, Sean? Okay, another one. Chris T. You know what? I think he should just read it.
Sorry. We've heard that NASA is the key to the Starshade moving forward. What is Northrop Grumman's role in development of the Starshade?
Who wants that? Alberto.
We are an aerospace industry, so we have built demonstrations of some of the hardware. We are looking at the engineering aspects of this to go forward. As I said, this is an integrated Northrop NASA academic team. So it's kind of hard to draw a dividing line as to what NASA is doing and what we're doing and what academia are doing. We're all in this as an integrated team, and everybody has contributed some aspect of both the optical performance, the deployment, and this sort of stuff. So it's not partitioned in that similar way. We are a single team.
Okay. So Alberto, you want to add?
No, I just wanted to add, the part of our core mission is to enhance discovery, right? And so that's how we do it. We do it with JWST, for example. We do it in many areas of science, and Starshade will be another example of how we fulfill that promise, of finding exoplanets, for example, in the future.
Okay. All right. Is there anything else, Isan? Give him the mic.
Mary Becker on YouTube wants to know, Starshade will work for stars out to what distance from us?
To what distance from us?
Somewhat of a fuzzy question, and
that
fuzzy
depends
answer.
on the diameter.
Yeah,
right?
I mean, it basically is how big of a telescope do you want to go for. When you get much beyond about 100 parsecs, it gets really, really tough. The habitable zone just becomes really close for all stars, and so something within 20 to 50 light years is probably going to be fairly straightforward over the next decade or two. Beyond that, it's a lot's going to depend on how big of a telescope you want to build and how big of a starshade you want to put with it.
Okay, awesome.
But we'll sample enough space to have a high probability of saying, does life exist outside the solar system?
There you go. So that's a good question. So I guess is that everything there, Ishan? Okay, I guess we'll go ahead and unless you guys want to address something that we haven't talked about, I guess we'll sort of close it there. Alberto, you have anything you want to add? Okay. All right, folks. Well, that's it for our first hangout from the AAS, the 225. I'll be joining. Come back. What time is it? In about an hour. About another little over an hour. I'll be setting up at 3:30 Pacific Standard Time to talk about the 25th anniversary, Hubble 25th anniversary image release. It's coming out in about 5 minutes. So we'll have Carol Christian, Zolt LeVay, and a few other people at the Institute to talk about that image. We hope you will also leave us comments and questions. And on behalf of the folks here at Northrop Grumman, Steve and Ron and Alberto, thank you all for watching. And as always, keep.
Not yet, not the space version at least. Okay. We've been doing some testing on the ground, and what we're doing there is we're taking a light source out to the desert. We've got a nice picture here. There's a light source over Ron's head over there, telescope in here, and what we're doing is we're using this bright light source to simulate a star. And we've got some other little light sources that simulate in the planet. We put a starshade, which is, about that big, a 1% scale starshade, something like that, in between the bright source and the telescope, and we're checking our imaging with that. And we're showing that the computer models that we have for how the optics will work are very similar to what we're able to collect, the images we're able to collect in the desert.
Okay, so we've got a proof of concept essentially already built.
Yes, absolutely. So one of the things with the starshades is as Ron mentioned, the very specific shape of it. We're trying to suppress the starlight to 10 to the 10, and that's a really difficult number. 10 to the 6 would be relatively easy. 10 to the 10 gets really quite hard. So there's a lot of questions about whether the model is going to be accurate. The optical model is accurate at that level. So there's some possible different shapes you can use. There's the issue of when you build this thing and you fly it in space.
With regard to starshades, I've been there since the beginning, when it was about 10 years ago when the concept first came into being. We did some stuff with the University of Colorado, and what resulted from that was this concept of a starshade.
Awesome. And also with me is Steve Warwick. He's an engineer building the thing. Hi, Steve.
Hi, how are you doing?
So tell us a little about what you're doing.
So most of what we're doing at the moment is testing the optics of the Starshade, seeing how the Starshade does what it's supposed to do, which is to block out the light of a star so that we can see the light from a planet, an exoplanet.
Well, welcome to both of you to our Hubble Hangout. I appreciate this, even though we're talking about Starshade. It is in fact a Hubble Hangout. So so Ron, let me get back to you a little bit. Tell everybody what this thing is. What are you doing? What is Starshade, and what are you hoping to accomplish with it?
Well, the big issue with seeing exoplanets, these are planets that are around stars outside the solar system. Planets are very faint, stars are very bright, so astronomers have been struggling for a long time with how to suppress that starlight and then see the planets around it. About 10 years ago, we came up with this concept for something that's very different from the traditional approach, which is to build an instrument and put it inside the telescope and get rid of the starlight through some sort of internal thing. This is a device that's fairly large, but it flies outside the telescope, and it blocks the light from entering the telescope and allows the planet to...
Let me know when you see it live. Hubble Hangout and Hubble. Hello, everybody, and welcome to the 225th meeting of the American Astronomical Society. My name is Tony Darnell. I work at the Space Telescope Science Institute, and we are here at the Northrop Grumman booth in the exhibit hall to talk about a really cool project called Starshade. And with me, again, after a long time, is my old friend Alberto Conti. Now, we've got this awkward thing going with the microphone. I'm going to have to give it back and forth to him. And in a minute, I'm going to let him speak to us. But first, interact with us. Send us questions. Talk to us on Twitter, Facebook, and G+, as well as the YouTube page from which this is being broadcast. This is on our Hubble site channel. We're looking at your comments. If you use the hashtag Hubble Hangout, we will see that on Twitter. And I've got lots of people looking up for those tweets from you, as well as the comments on G+ and Facebook. So ask us questions about Starshade. You don't know what it is? We're gonna find out. So I got people here from Northrop Grumman to tell us, but before I introduce them, Alberto, it's good to see you again.
So you have to do this, which is a little awkward, isn't it? I have to wait to respond to you. It's great to see you again. We haven't seen each other for quite some time actually here, And so this is actually routine for us. So we should do this often, the old days. So we're going to do this. I wanted to mention we're going to do this throughout the week. So you're going to do it half and half at the Northrop booth and half at the Space Telescope booth, which is fantastic. So we're going to talk about lots of topics. Starshade is just the first one. We have great people here from Northrop Grumman to tell you exactly what they are, and I'll leave it up to you. Let's get it on.
Yeah, so I'm glad. So you need to tell people what you're doing at Northrop, though. I don't think people know. What did you do? You left the institute to do what? What are you doing now?
I have a little strange title. I'm an innovation manager for civil air and space. So I work in the business development organization. So I have in my portfolio things like JWST, which I support. I can continue to support, but also things like we're going to talk about today, Starshades and maybe next generation flagships. So it's a very, very interesting job, very, very hectic, and it's I love it.
Yeah, well, we miss you at the institute, that's for sure. So, okay, let's get to the meet. Oh, one more thing. If you want to keep track of where we're going and what hangouts are coming next, the best way to do that is to follow our Facebook page, Hubble Telescope. Also follow NASA Hubble. He'll be tweeting on that, as well as I'll be posting the events on Google+. So that's how you're going to know which hangouts are coming up next. All the ones for today are already posted. We have a whole nother slew of them planned tomorrow. So. Okay, let me get to our guest. I have with me an astronomer from Northrop Grumman. His name's Ron Paladin. I had to look at your. I'm so bad at names. He is an astronomer at Northrop Grumman. Welcome. So tell us a little bit about what you're doing.
I'm the science manager for Northrop Grumman, and will come through unencumbered. So it's sort of like putting your thumb in front of a bright light to block out the light so you can see what's around it. So yes, like that. And so this is just a very special, unusually shaped thumb.
I'll say.
It looks like a daisy with petals and such. And that's a mathematical design that allows this spot that it creates to be very, very deep and very dark. And so think of it as a traveling dark spot.
Okay, well, that's a really interesting concept. I mean, a lot of times, I know what you're saying about sometimes they have telescope tubes or optical assemblies will put something called an occulter in the light path to kind of block out just a little disc. Usually it's a cone shape or something like that that just sort of blocks out the bright spot of the bright star. Solar telescopes have these all over the place to block out the disk of the sun so they can see the limb and also the solar corona. So the stars, is it because the stars are so far away that the planets are, I mean, you can still resolve, even at, say, dozens of light years, planets that might be in orbit around a star with the light blocked?
Yes, I mean, the big issue, and it is a hard thing to do, it's basically like trying to image a firefly a few centimeters from a searchlight. So it is a very, very difficult thing to do. But yes, with a large enough telescope and with something that can block out this light, the planets are going to be observable.
Awesome. So Steve, let me get you in on this. So have we started building it yet?